we noticed that for the Hopf bifurcation, the equation that we derived with the multi-timing had a relatively special form, right? It was this form where in particular the nonlinear term had only a cubic nonlinearity, and it was this special form with just A absolute value squared A. Whereas when you did the Zener manifold reduction, we didn't get that right away. We had to do a near identity transformation to get to this form. So we'd like to understand somewhat better where that special form comes from. And it turns out it is associated with symmetries. And so let's look at that, because those symmetries, or symmetries in general, can be very powerful when you want to derive equations, bifurcation equations, particularly when you do multi-scaling. Whenever you have to choose the scaling, the symmetries can help you significantly to pick the right scaling. Okay, so let's first note what the special properties here are. You can notice actually following this equation doesn't change if you replace A by e to the I phi, right? All terms change the same way. And so it says the equation is equivariant under that transformation. And we'll see that this is related to the fact that the original equations were independent of time, meaning they were constant coefficients that were invariant under time translations. So when we have t going to t plus delta t, that induces, as one says, this action on the amplitudes. And in a nutshell, we'll enlarge upon that in a moment, but in a nutshell, it is all related to the fact that we have y was given essentially by epsilon times a of slow t times e to the I omega t times some eigenvector plus higher order terms and complex conjugates. And so this is y of t. And when you look at y of t plus delta t, that's going to be epsilon of a capital T e to the I omega t plus delta t v plus stuff, which you can write as epsilon times a of t e to the I omega delta t times e to the I omega t v plus stuff. And you see what happens when you make a shift in the fast time. What happens, you pick up this factor e to the I omega delta t, which is a phase factor for the amplitude A. And so that's where this invariance comes from. And it all rests upon that the slow time is actually not shifted in this process, because we really are assuming that t and capital T are independent of each other. Okay, so let's enlarge upon that. Let me just remark, so we'll use these symmetries later, or extensively then, to investigate oscillators with forcing, various kind of forcing. So it's actually quite rich what the behavior one can get there. And the symmetries will help us a lot to do that. So in the notes, I have like a number of examples that talk about where forcing and resonant forcing in particular is important, detrimental, useful, and all kind of things. And I recommend looking at that. There are some links to videos which are quite nice and stuff. I will not talk about that here. I'll just focus on the math here. Okay, so what do we want to do? So let's now enlarge upon that and make it more clear. So when we do our analysis, and this is now general, this is not specifically, the principle is not specific to Hopf bifurcations. We'll use it for the Hopf bifurcation, but the principle goes further, and we'll use that later also in other situations. Anyway, we do a weakly nonlinear analysis. And right now, I'm always going to assume we're going to do multiple times scaling. And so what we will get, if we do that, there will be some amplitude A, right? There will be some amplitude A, and we'll derive an evolution equation for that A, and it will be always a Taylor expansion, because we do weakly nonlinear, we expand in A. So the equation in all generality, if there's just a single A, will be given by some F of A and also a conjugate, right? So that's the general equation that we will get. And the observation we made is when we did the calculation that we didn't get a very general F. We just got an F that had only cubic nonlinearities and actually only one of them. no quadratic. Quartic, we don't know, we didn't go that far, but that's what we found. And so we want to see what are the rules that pick which nonlinearities can actually show up in F. And so as I said, in this case, we're focusing on this time translation symmetry, which I wrote down here already. So we're thinking about a system where the coefficients are independent of time, constant coefficients. And so therefore, the system is invariant under time translations. Or in other words, if y of t is a solution, then y of t plus delta t is also a solution for arbitrary delta t. Okay, and so what we saw now also in this little calculation here is that if you write down y of t plus delta t, well, you can write it in this form, where if I just want to add, to make the notation clearer, we get sort of something like this, which is pretty much the same as for y of t, except that a is replaced by this factor here. And so what we can say is that is the following few statements. So if y of t is a solution, so we have if y of t is a solution of the original equation, then a of t is a solution of the amplitude equation. I mean, that's the point of this whole analysis, right? Amplitude equation. Okay. Now, we know because of the time translation symmetry, if y of t is a solution, then y of t plus delta t is also a solution of these original equations. Okay. Now, as we saw here, when you do the calculation with y of t plus delta t, it's the same as if you essentially did the calculation as you did it for y, but instead of a, you have a times e to the I omega delta t. So let me maybe, yeah, that's fine. And so we know that if y of t plus delta t is a solution, then a of t times e to the I omega delta t is a solution of the amplitude equation. And it's the same amplitude equation because the amplitude equation itself, meaning its coefficients, they don't depend on delta t or the fast time. It only lives in the slow time. And so therefore, we know that if the shifted solution is shifted y is a solution of the original equation, this phase shifted object must be a solution of the amplitude equation. But it's the same amplitude equation that A solves. And so therefore, we also have like an equivalent sign here that if A of t is the solution of the amplitude equation, then A of t times e to the I omega delta t is also a solution of the same amplitude equation. And so we can say that the following, if the original equation, let's write it that way, original equation is equivariant under t to minus t to t plus delta t for all t delta t, meaning the delta t is arbitrary. And equivariant means, as I mentioned before, equivariant means that all terms in the equation transform the same way. They don't have to stay put, they can't change, but it's the overall equation, they all change the same way. Okay, so that then implies that the amplitude equation is equivariant under what object, what transformation? It's this transformation from A to A times a phase shift. It's under this transformation A going to A times e to I delta phi for arbitrary delta phi. So that's what we conclude from this argument. And so that restricts the equation, the form of the equation that you can get substantially, right? In general, we have an arbitrary polynomial, but actually they all have to satisfy this condition that they're equivariant under this thing. Let me mention a little bit now more generally, or enlarge upon it. We did notice that when we did our center manifold calculation, we did not get this equation here. We got an equation with quadratic nonlinearities and all kind of stuff. We only got this normal form after normal form transformation using the identity transformations. So this is related to the fact that when I say here that we're doing this phase shift, and this shift in time rather, and that this induces this phase shift in A, well, this makes use of the fact that in the multitiming, the fast time dependence is strictly periodic, right? So it's strictly periodic, and only therefore, when you change time, shift time by an amount, that amounts to shift the phase by an amount, only because it's strictly periodic. Now, in reality, I shouldn't say in reality, I mean, this is not an exact statement because there is no two different times. There's only one time to be had. So when you do the center manifold reduction, where you don't do in two different time scales, there is, when you do a time shift, there is no phase shift induced because the dynamics may not be periodic. So as a matter of fact, the dynamics for A need not be periodic, right? We get a differential equation for A, and there could be a growing amplitude, could be a decay, whatever. It's just a general differential equation. And so, and we did not, therefore, apply anything, a time shift on the slow time. So that's where it's actually an approximation. And so in this case, the symmetries is not exact. This form here is not what you get exactly, but rather you get it only in normal form. And we saw that what that means is that in principle, there's also all the other terms, but by a near identity transformation, you can push them, well, looks like removing them, but they're not going away. They're just pushed to higher and higher orders. So it's not an exact transformation. And for certain subtle results, like if you have like heteroclinic orbits, stuff which is clearly not periodic, then these issues can become important. But for our purpose, this is perfectly fine. It's a very simple way to get an idea of what the final form of the equations that we're talking about will be. And once we have that, it's very straightforward to get the scaling. Now, the fact that this is not exact, that's related to that we're talking about general dynamics. There's the other symmetries which operate differently. You could have spatial translations, and the system could be strictly spatially periodic, in which case the symmetry is exact. Or you could have other symmetries, reflection symmetries or permutation symmetries, and all these symmetries will induce something like this. Talking about inducing, just in terms of words, what one says is that the symmetry, the translations, they induce an action on the amplitude. So the translation delta t in time induces the action A going to A e to the I delta phi on A. And the general statement is that if the original equation have a certain symmetry, that symmetry will induce a certain action on A, and that will depend very much on the system, on the bifurcation. But what will not depend on that bifurcation is that whatever that action is, the resulting amplitude equation has to be equivariant under that action. Okay, so that's the general statements. And in the next video, we'll use that explicitly, first from a general point of view, and then we'll eventually look at a couple of examples where we can make very good use of that.